Today we're going to look at simplifying radicals. So the product property of square roots. So it says for any numbers a and b where a is greater than or equal to 0 and b is greater than or equal to 0, the square root of the product ab is equal to the product of each square root. So that's just saying you can multiply the numbers together and then take the square root, or you could take the square root of each number and then multiply and you're going to get the same thing. So for example, if we look at the square root of 4 times 25, if we multiply 4 times 25 first, that's the same thing as saying we have the square root of 100. Well, the square root of 100 is 10. Or we could look at them separately, and we could take the square root of 4 first, which is 2. Then we could take the square root of 25, which is 5. Then we can multiply those together, which still gives us 10. Notice we get the same answer either way. So these first couple examples are just perfect squares. So the first one we have the square root of 36. Well, the square root of 36 is 6 because 6 times 6 gives you 36. You have a pair of 6's. Same thing with square root of 16. The square root of 16 is 4 because 4 times 4 gives you 16. A pair of 4's multiplied together gives you 16. Now, not all radicals are perfect squares. So if the radical is not a perfect square, there are two different methods that you can use to simplify. You can either find the perfect square within that radicand and simplify those, or you can do a prime factorization of the number and then group the pairs of the same number. So this first example, I'm going to show you both methods and show you that you get the same answer either way. So I'm going to start with the perfect square method. So if I have the square root of 72, that's not a perfect square. There's not a whole number that you can multiply by itself to give you 72. So I'm going to simplify this. I want an exact answer. So I could say, well, 72 is the same thing as the square root of 36 times 2. Well, 36 is a perfect square. So the square root of 36 is 6, and then notice all I have left over is that 2. But I can't do anything with this 2. I can't take the square root of that. So that one you'll just leave. So the square root of 72 is 6 square root 2. Now, if you don't know all your perfect squares, you might need to do a factor tree. So I'm going to show you that you're going to get the same answer. So if we do a factor tree, let's just say I use 36 and 2 again. Well, I can break down 36 into 6 and 6 with a 2 left over. I can break down 6 into 2 and 3, 6 into 2 and 3, and then bring this 2 down. Now I'm looking for pairs of numbers. So if I look, I have a pair of 2's, and I also have a pair of 3's. So that means I can bring a 2 to the outside, and I can bring a 3 to the outside, which when I multiply together, that gives me 6. And the only thing I have left over is this 2, so it stays underneath the square root symbol. So notice you get the same answer either way. The same thing here. I'm going to do both methods just to show you that you're going to get the same answer. So square root 48. So square root 48 is the same thing as the square root of 16 times 3. 16 times 3 will give me 48. Well, the square root of 16 is 4, so I can bring out a 4, and then this 3 would be left over. So 4 square root 3. Now, if you don't know that, let's come over here and let's try to do a factor tree. So let's just use, 8 and 6 here. That will still give us 48. Neither one of those is a perfect square. So let's break down 8 into 2 and 4. Break down 6 into 2 and 3. Bring down that 2. We can break 4 into 2 and 2. Bring down that 2 and bring down that 3. So now we're looking for pairs of numbers. So I have a pair of 2's and I have another pair of 2's. So if I bring each of those 2's out, and then I have this 3 left over. Well, 2 times 2 is 4, and I have that square root 3 left over. Notice you get the same answer, so do whichever one's easiest for you. Now we can use that prime factorization method with other roots as well. So example 3 here, notice how on this one you have this little 3 outside of your symbol. So you read this the cube root of 125. So we're still going to use a prime factorization, but this time we want groups of 3. Whatever that root is, that tells you how many numbers to look at, or to find rather. So 125, let's just start with our prime factorization again. So we could say that this is the same thing as 25 times 5. I can break down 25 into 5 and 5 and bring this 5 down. So now since I had this 3 out here, that means I need groups of 3. So I have a group of 3 of 5s. So that means the cube root of 125 is 5. And there's nothing left over, so your answer is just 5. Okay, so same thing here. This time we have cube root again, since the index, the little number on the outside of the symbol is 3, so the cube root of 250. So let's just do prime factorization. So we're going to start with the cube root of 250. So let's break down 250. I could say 25 times 10. I can break down 25 into 5 and 5. And I can break down 10 into 5 and 2. So since this is cube root, I need groups of 3. So I have one group of 5s with this 2 left over. So that means my answer is going to be a 5. You take the group out. Whatever's left over goes underneath the symbol, but remember this time you had cube root. So this is 5 times the cube root of 2. Okay, same idea on example 5, but this time you have the 4th root. Notice this number on the outside is the 4th root. So you need groups of 4. So let's break down 64 with our prime factorization. So I'm just going to start with 8 and 8. I can break down 8 into 2 and 4. I can break down 8 into 2 and 4 again. Can't break down 2. I can break down 4 into 2 times 2. Bring that 2 down. And 4 into 2 times 2. So once again, our root was the 4th root. We have a 4 out there, so you're looking for groups of 4. So 1, 2, 3, 4. Here's a group of 4 with these 2 left over. So one number from the group comes out. The ones that are left over you multiply together. But once again, this was 4th root. So this is 2 times the 4th root of 4.